Okay, welcome back everyone. Let's welcome the last speaker of today, Tobias Diez from TU Delft, and he's going to talk about infinite dimensional symplectic geometry.
Thanks a lot for the introduction, and thanks a lot, of course, for the invitation, and more of kind of like thanks for the organization of this very interesting and nice conference. I would like to be in Vienna, but given the circumstances, I sadly can't. I'm only joining virtually. Today's talk, because it's the last for today, I've said I don't want to focus too much on details and give more like a broad overview of different aspects of symplectic geometry in infinite dimensions. So in this viewpoint will be kind of like similar to Alex's talk yesterday morning. So not going into that many details, but just giving a bigger overview. So today's talk will be just like a journey through the symplectic geometry in infinite dimensions. And the first step will be that I explain you the technical problems that you have to face if you go to infinite dimensions and want to do symplectic geometry there. So a few things that you're used to in finite dimensional constructions don't work, and you have to come up with new constructions, and some of them are more like functional analytic of nature, and some of them have a more geometric flavor. These new constructions that you have to come up with. And the goal for today will be to discuss symplectic reduction in infinite dimensions. But first, before we go together on this journey, I want to start with a bit of general motivations why infinite dimensional symplectic geometry and also infinite dimensional Poisson geometry is very interesting, and why should you kind of like study these kind of objects, even though if you're, for example, more interested in finite dimensional objects. Let me start with a bit of motivation. And the first example I want to look at is some examples coming from physics, or more especially from hydrodynamics, where common constructions that you use from finite dimension Lie Poisson or Poisson geometry have some very nice interpretations and consequences for hydrodynamics. So that's a pretty old picture already that goes back to Arnold and Maaßen and Weinstein. And the point is that you start with some Lie algebra. And as already discussed yesterday, once you have a Lie algebra, then you get a Poisson structure on the dual space. So that's in particular given by this formula, where you have the Poisson tensor is defined by fixing some element in the dual of the Lie algebra, and then it needs to eat two tangent vectors, or in this case, two elements of the Lie algebra. And what you do is you take the commutator of these two elements of the Lie algebra, and then plug them in the co-vector that you're given. And that's then a Poisson tensor, as you can verify. And the picture in hydrodynamics is that the Lie algebra is the Lie algebra of vector fields that preserve a volume form. So you have normally it's three-dimensional, a manifold. You can have boundaries, but for the sake of this talk, I want to ignore all boundary contributions. So we have a three-dimensional manifold and a volume form on the three-dimensional manifold, and we look at all the vector fields that have vanishing divergence. And this is a nice infinite dimensional Lie algebra. And the dual space is given by essentially by one forms. So if you have a vector field and you want to pair it with something, the natural candidate would be that you take a one form and then pair this vector field with the one form by inserting it, and then you get a function on M, and then you integrate this function using this volume form that you are given over M. So I'm assuming M is compact, so that we don't have to worry about boundary conditions at infinity. And because our vector fields had divergence free, or like vanishing divergence, you see that this pairing is degenerate and vanishes if you add plug in exact one forms, so that you can then identify the regular dual with the one forms modulo the exact ones. And I also want to ignore all topological effects, so I'm assuming that the first Betty number vanishes, and in this case we can just identify this quotient of one forms modulo the exact forms by the space of exact one forms, exact two forms. Sorry. And then this construction gives you a dual, a Poisson structure on the space of exact two forms. And what can you do if you have like a Poisson structure? Then you would like to look at dynamics, of course. And so if you have like a Hamiltonian function, which is in this case just a smooth function on the dual of the Lie algebra, then we can write down the so-called Poisson equation, which is given by the evolution of a function f is given by the Poisson bracket with this Hamiltonian that we have chosen. And if you do the same for the hydrodynamics picture, namely that we choose the energy to be just the L2 norm of this one form, the two form, sorry. Then we get the Euler equation in its vortice formulation. So usually the Euler equation is written for a vector field, so that's the small v here, and the vorticity of this vector field is given by first you're using a metric on M to get a one form from the vector field, and then you take the exterior derivative to get the exact two form, and this is the so-called vorticity. And then if you write down the Poisson equation, in this particular case, they take this form, and this is the Euler equation in this vorticity formulation. So you see that just like rewriting or considering the Poisson equation for this particular case, you recover the Euler equation. So that's a bit similar to what Alex mentioned in his talk, that you can view the Euler equation as a geodesic equation on the Lie group of the volume preserving diffeomorphisms. And that's essentially, if you have an equivariant flow on the Lie group, then you can pull back everything back to the Lie algebra, and what you get is then a flow on the Lie algebra. And that's essentially this Euler equation in the vorticity formulation. So you see that the Euler equation is equivalent to a particular example of a Lie Poisson equation. And then there are a lot of interesting things that you already get out from like the general theory. One of them is, for example, that you easily can verify generally that the solutions of the Lie Poisson equation preserve co-adjoint orbits. And if you translate this to the hydrodynamics picture, then this is equivalent, or at least implies Kelvin's circulation theorem, which says that certain circulations, which are like the flows along one forms of the vector field, it's a circulation, and they are preserved in time. And that's a consequence out of this preservation of the co-adjoint orbits in the general theory. So you see that general constructions in Poisson geometry have a very nice interpretation in infinite dimensions if you apply them, for example, to hydrodynamics. And another really nice construction is the so-called symplectization. So there's this structure like that you have the flow on the dual of the Lie algebra, and what you would like to do is that you write them as a symplectic Hamiltonian system, and the flow on this Hamiltonian system. And what you can do there is, for example, that you have a symplectic manifold and some Hamiltonian there, which are denoted by the small h. And if you then have a Poisson map to the dual of the Lie algebra with this Lie Poisson structure and the given Hamiltonian, then you can easily prove that solutions of those on this symplectic manifold project down to solutions of the Lie Poisson equations. And so one way to solve the Lie Poisson equation would be then to rephrase them in terms of this symplectic manifold and solve the equations there, which sometimes is easier. And then you can project them down and to get solutions of the Lie Poisson system. And in hydrodynamics, if you do these construction, then you recover what is called the Clebsch variables. So in this case, we have the symplectic manifold, which is the cotangent bundle of all smooth functions on a manifold. So you can identify them just as two smooth functions on your manifold, which I denoted here by psi and eta. And this map to the exact two forms, which is the dual of the Lie algebra, is just given by taking the wedge product of the exterior derivatives. And if you write this in this form, then you see that the Euler equations really get, in terms of these variables of psi and eta, really just get Hamiltonian equations. And you can rewrite this also in terms of the vector field, which is probably the form that you're used to more if you talk about Clebsch variables. So that's a very nice construction where the symplectic and the Poisson geometry interplay and give you interesting results about hydrodynamics. And this story also goes a bit further, where we, if you leave kind of like the very simple example of a linear Poisson space and go the next step further, which is the so-called Poisson Lie groups. So that are Lie groups for which have a, first of all, Poisson structure, and what you require is that a multiplication map on the Lie group is a Poisson map. And there's an infinitesimal notion of this, and this is called Lie bi-algebra. So that's two Lie algebras, which are in duality. So one of them, you have kind of like a dual pairing between the two Lie algebras. So that's why I denote one of them with a G star, because you can think of them as like the dual of each other. And there's also some requirement about compatibility of the Lie brackets of the two Lie algebras, but I want to ignore kind of like the technical part. And then there's a theorem which goes back to Lu and Weinstein, which says that once you have a pair of Poisson Lie groups, so that's two Poisson Lie groups, and the Lie algebras have a pairing between them. If you have such a Lie groups, then you can take the derivative essentially at the identity of the Poisson structure, which has to vanish at the identity, and then the linearization gives you a Lie bracket on the dual. So in this way, you can get from Poisson Lie groups to these Lie bi-algebras. And conversely, there's an integration theorem that says that under certain conditions, for example, simply connected and connectedness, on the groups, you can integrate this bi-algebra structure to Poisson structures on the Lie groups. And interesting enough, there's a further integration possible, namely that you can integrate Poisson Lie groups to have certain actions. Namely, you have an action of G on its dual, and conversely, you have also an action of the dual on the G itself. And they are, we call them a conjugation action because they integrate the co-adjoint actions. And there's a derivative procedure that you go from, or like the integration procedure is that what is called the trussing transformations. So you get a certain flow on the Lie groups, and you can integrate them to an action under certain conditions. For example, if this flow is defined for all times. And conversely, if you have these trussing transformations or conjugation actions, as we call them, also you can take the derivative and then get a Poisson Lie group structure. So there's this nice hierarchy of conjugation actions, then Poisson Lie groups, and then Lie bi-algebras. And so let's apply this to hydrodynamics, where we take the following action as the co-conjugation action, namely that we consider the diffeomorphism group that preserves the volume form. So that's our G, and it acts naturally on the group, which is here denoted by H hat and with a 2, and it has some kind of like U1 there, and the U1 denotes kind of like stands as a reminder that these ones are so-called Checker-Simons differential characters, or if you never heard about these, then you can just think of this H2 as the group of all principal U1 bundles over M up to some gauge equivalence, so just like U1 gauge transformations. And then connections on these bundles. So it's an equivalence of a bundle plus connection modulo gauge transformations. And these form a group under tensor product. So you have this nice abelian group. And as a co-conjugation, you just take the pullback. So if you have a bundle and a connection and a diffeomorphism, you just take the pullback of this bundle and the connection and to get another bundle with connection. That gives you this action of the diffeomorphism group. And then as the other action of this, the dual action, we just take the trivial action. So there's nothing interesting happening that the dual space is not acting on the diffeomorphism group. So in this case, we kind of like get integration of this dual pair of Lie algebras that we started with. You meet the Lie algebra of the diffeomorphism group is just our volume preserving vector fields that we already saw. And the Lie algebra of this Checker-Simons differential characters, or the principal bundles with connection, is this quotient space that we already saw. And the way you can think of this as the Lie algebra is that if you have a connection on a principal U1 bundle, then every other connection differs by exactly a one form on the base. And then the gauge transformations are acting exactly by taking the exterior derivative. So that's you can think of this one forms modulo exact forms exactly as the space of gauge connections on a trivial bundle modulo gauge transformations. So in the sense, that's the Lie algebra of this H2 hat. And then if you do this strategy that you started with some actions of the diffeomorphism group on this H2 hat, and then take the derivative, then you end up with this following formula, which is a Poisson structure on the space of bundles. And so the viewpoint here is that the Poisson tensor is something that is given at a point. So that's this first entry, which is the H, which is a connection on a principal bundle, on an equivalence class to be exact. And then this tensor, Poisson tensor, needs to eat two elements of the dual, and the dual is identified with the volume preserving vector fields. So in this sense, you get a Poisson tensor that has this form. And if you calculate this, what is this? If you start with the natural pullback action and then calculate what under this formula for the conjugation action to the Poisson Lie groups, if you calculate this, you get this this particular formula where you take the curvature of the connection, which is a two form, and then you plug in the two vector fields into this two form, and you get a function, and then you integrate this function over your manifold to get a real number. And this is the Poisson structure on the space of differential characters. And the interesting part here is that you recover in this way the Lichner-Horowitz co-cycle. So there's this famous co-cycle on the space of volume preserving vector fields, and that's exactly of this form, except that you add an arbitrary curvature or two form there. And now we have this particular assumption that this two form that we insert in a general Lichner-Horowitz co-cycle is given as the curvature of a differential character. So, and that's a kind of interesting point, because we know that these kind of co-cycles are integrable to also Lie group co-cycles. So it's kind of interesting that you can integrate these co-cycles in two different ways. One is in the sense of the co-conjugation action, that are just like coming from the diffeomorphism action, and then also that you can integrate these ones to Poisson or like as co-cycles on the Lie group of volume preserving diffeomorphisms. And an open question in this context is, for example, can you give non-trivial Poisson structures on the diffeomorphism group, or some volume preserving or some plectomorphism groups? So here it was really that we used natural action of the diffeomorphism group on something else, and then by this construction we get a Poisson structure on this other space. And it would be nice to have like a dual construction where you have something acting on the diffeomorphism group, and then by this construction get some Poisson Lie group structures on certain diffeomorphism groups, which would be definitely of interest if this is possible or not. So that's one of the examples coming from hydrodynamics. And there are different examples which are mainly coming from gauge theory. And the classical example is going back to Attila Bott, and there's a similar paper from the 80s. And what they studied is the following. So you are given a two-dimensional closed manifold and a principal G bundle over this surface. And what you're looking at is the space of all connections, which is an affine space modeled on one forms, and this one form takes values in a joint bundle. So that's just like, yeah, the space of connection is an affine space over this space. And Attila and Bott defined the following symplectic structure on C, which is given by that we, first of all, we have a connection that we need to fix as a base point, and then we add two elements of the tangent space, and because it's an affine space, the space of connections, they are just like elements of this vector space. So we have two one forms with values in the adjoint bundle, and what we're like doing is we take the wedge product to get a two form, and then we take the trace to get really a two form with values in the real numbers. And then we can integrate this over our two-dimensional surface. And this M here should be actually a sigma. I'm sorry for this. So everywhere we see an M on the slide, that's actually supposed to be this two-dimensional surface. And then you can verify this, that this is really a symplectic structure on the space of connections. And you can study the action of the gauge transformations, which naturally acts on connections, and you can verify they act symplectically, and moreover, you can calculate the momentum map. And it turns out that the momentum map is given by the curvature of the connection. And this has important consequences. For example, you can look at the symplectic quotient, and this would be then the space of free connections modulo gauge transformations. And if you view this as a kind of like as a nonlinear complex, in the spirit of what a unit told us yesterday, that you have gauge transformations acting on the space of connections, and then because the momentum map is equivariant, you get a map from connections to the two forms with values in the adjoint bundle. And this complex, if you linearize it, you get the Lie algebra of the gauge transformations, which are just the sections of the adjoint bundle, and then the linearization of the space of connections is given by the one forms with values in the adjoint bundle, and of course the linearization of two forms stays the same. And the linearization of the action turns out to be just the exterior derivative with respect to a connection that you choose to as the base point for the linearization, and also the derivative of the momentum map or the curvature, if you want, is also the exterior derivative. So what you see is that you get something that resembles the Hodge complex in the sense that it's kind of like the non-abelian version. So if you have if you remove the A there, then it's just really the normal Hodge complex. And now I changed my chair, so I'm not sure if you actually can still see me. So I'm going back up again or not. Okay. Yeah, if you can't see me, then wait a second. Yeah, I think it's still fine. Yes, yes, and in the sense, because it's the linearization of this Hodge complex, you can view this symplectic quotient on the modular spaces of flat connections as a non-linear version of a non-abelian Hodge theory. And so this means that you can extract some geometric invariants, for example, that are refinement of the traditional Hodge invariants. So you get a refinement of the Betti numbers. And for example, one method to construct them is by looking at symplectic quantization, geometric quantization of this modular space, a flat connection, which by this procedure of symplectic reduction inherits symplectic form. And these these invariants are then refinement of the Betti numbers. And that was used originally by Attia and Bott. And there's a different story that comes from looking at Young-Mills equations. And in this time, we don't look at something over 2 dimensions, but really over the 4-dimensional version. So here are the Maxwell equations written down in the differential form. So E is just a 1 form and B is a 2 form in this language. And what you of course know if you study Maxwell equations, the first thing is that you have this equation that the 2 form is closed. So what you do is that you solve this equation by going over to the space of connections, or in this case, just 1 forms. And then you set dA equals B, and then this equation that you that B is closed is automatically solved. So what you end up with is kind of like this reduced setting of equations. And there's a nice symplectic interpretation of the Maxwell equations, or if you want to, the non-abelian version would be the Young-Mills equations. And the story goes as follows. Namely, you consider the phase space, which is just a cotangent bundle of the configuration space. And because everything is vector spaces here, this is nothing else than the space of you have pairs essentially, and one of them is a connection or 1 form, and the other thing is the E, which is also a 1 form. So the 2 variables A and E, and both of them are living as you can view them as points in the phase space. And of course, we also have a natural action by the gauge transformations, which are in this case just U1 valued functions. And they act symplectically on the phase space, and the momentum map you can calculate, and it turns out to be exactly this equation, or this the left-hand side of the Gauss law is exactly the momentum map. So what you see is that the Maxwell equations in this formulation have like 2 ingredients. In the first equation is the Gauss constraint, which you can obtain as a momentum map constraint, and then you have 2 dynamical equations, and these ones are just Hamiltonian equations for a natural Hamiltonian, which is given by essentially the square of B and plus the square of A, or the norm. And so you can do a lot of different stuff with this interpretation. And one of them, for example, is that you could ask yourself, okay, I want to quantize, for example, Maxwell or Young-Mills equations. And then this would be one a particular approach where you say, okay, I know that these equations have a symplectic interpretation. And for example, I want to use deformation quantization or geometric quantization in order to construct a quantum field theory for these equations. And then there's, of course, a very interesting question is, for example, if you do first quantization and then do a quantum reduction of the symmetry for the gauge transformations, or if you do this the other way around, where you first do symplectic reduction to quotient out the symmetries and then do quantization, and does this, for example, commute, which is a very well understood or well studied question in finite dimension, but is completely open in infinite dimensions. So that would be, for example, one particular case where the finite dimensional constructions should be further developed also in infinite dimensions, because they have like practical applications in quantum field theory. And here's one of them. So these are all things, applications of infinite dimensional Poisson geometry and symplectic geometry. And now that I told you kind of like why we should embark on this journey, the next step would be to explain you what kind of problems you are facing if you go to infinite dimensions and certain constructions that you're used to in finite dimensional don't work any longer. And I concentrated mostly on one particular problem, and that's the problem of that you have to deal with weakly symplectic forms. And so first of all, we fix some infinite dimensional vector space. And for the sake of being kind of like not being too pedantic about the infinite dimensional formalism, I'm assuming that this one is a Banach space. So usually you actually want to go to Fréchet spaces because you want to have actions of diffeomorphism groups, and then these are no longer really fitting in a setting of Banach spaces. But for the sake of being kind of like a bit more clearer, let's assume for now that everything is a Banach space. So we fix the Banach space, and then we have a bilinear form, which we of course want to be our symplectic form. And so we assume it to be separately continuous, and then we get a map which is the so-called musical isomorphism in finite dimensions. So what is this doing? If you have a vector in V, then you plug it into your symplectic form, and then you get a dual element. And because we assume that the bilinear form is continuous, this takes values in the continuous dual. And in finite dimension, you say that a symplectic form is something that is a bilinear form, which is antisymmetric and which is non-degenerate in the sense that this omega flat is an isomorphism. But it turns out that in infinite dimensions, almost no of the symplectic forms are non-degenerate in this really strong sense. So it makes sense to differentiate between symplectic forms that are only weakly non-degenerate in the sense that you require this omega flat to be injective. And then there's this stronger notion of symplectic forms for which you require that omega flat is actually bijective, as in finite dimensions. And as I said already, the point is that a lot of symplectic forms that you naturally encounter, for example, in hydrodynamics or in gauge theories, are actually only weakly symplectic. And the point is a bit that, in practice, you handle this V as kind of some form of a function space, and then the dual of the function space would be something like distributions, but the omega is usually some form of integration. So what this means is that if you have this omega flat, then it's some kind of inclusion of functions into distributions as regular integration valued distributions, but you never get all of distributions. So that's kind of like usually the reason why omega flat is only injective and almost never bijective. And so you say, okay, good. Well, I mean, we now have this a different structure, but we just say, okay, like we work with weakly symplectic things and everything works right. And the problem is, nope, everything kind of like does not work. And actually many things that you use from finite dimensional symplectic geometry work for strongly symplectic forms, but no longer for weakly symplectic forms. And one of the examples is related to the symplectic orthogonal. So what is the symplectic orthogonal? Is that you have a subspace of your symplectic vector space, and you consider it all these vectors that are, if you pair them with the symplectic form, are vanishing for all elements that you fixed in your subspace. So that's the orthogonal with respect to the symplectic form. And in finite dimensions, you really can calculate very easily that if you take the double orthogonal, so you take the orthogonal once and then a second time, then you get exactly the same space. And in infinite dimensions, there are really strange things happening. namely that if you have only a weakly symplectic form, then there exists a proper subspace, such that if you take the double orthogonal, you get the whole symplectic form, symplectic space. So so it's really far away from being the X again. So it's actually the whole space. So it's quite strange thing to happen if you consider weakly symplectic forms. And the proof is actually not that hard. So let's look at it. Because our symplectic form was only weakly symplectic, means that there exists a non-vanishing element of the dual space, which is not lying in the image of this omega flat. And then we can choose X to be just a kernel of this one form. And then if you calculate what the symplectic orthogonal of this X is, then you get by the definition of the orthogonal the following equation. And then you see that they have to vanish for all X in the kernel. And what this means if you rewrite this equation is that this B has to be in the inverse image under the omega flat of the kernel of alpha, and they're the annihilator of the kernel. And then you use think a bit, and then you see that the kernel, the annihilator of the kernel, is exactly again a multiple of alpha. And but by assumption, alpha was not in the image. So if you take the inverse image of this space, you get a 0. So the symplectic orthogonal of the space is 0. And then if you take the symplectic orthogonal of 0 again, you end up with the whole space. So we found now a proper subspace X, such if you take the symplectic double orthogonal, you get the whole space, which is really not what you would expect in finite dimensions. And this small exercise about double orthogonals is also coming in kind of like in applications that you want to consider. So there are really actions where you really see this effect that you want to take symplectic quotients, and then you need this statement, and you want to say that, okay, take the double orthogonal, and then it turns out to be actually not the space that you started with, and then a few constructions in symplectic reduction go wrong. And I come to this at a later point again. And there's something else that fails for weakly symplectic forms, and that's the Darboux theorem. So as a reminder, the Darboux theorem says that if you have a symplectic form in finite dimensions, which might depend on some point, then locally you find different morphisms that you can make the symplectic form constant. And so what goes wrong if you consider weakly symplectic forms, and that's a counterexample that was originally due to Marston. It's also pretty old already. So what can go wrong is that if you have the Darboux theorem, then this omega flat that you consider here as a family parameterized by some points, that they have to be constant. Because if the Darboux theorem holds, then you find a diffeomorphism which conjugates essentially this omega flat, and then you see if kind of the range of this map has to be constant in particular. But there's a pretty simple example that you can construct families of points where the image jumps around. And one particular construction that was given by Marston is the following, that you consider the Hilbert space and some compact, self-adjoint, and positive operator K that acts on the Hilbert space, and you require that the image of K is dense and a proper subspace. So I think like one of you can, for example, choose this particular example of K in which essentially some form of the Laplace operator for the Hilbert space of square integral functions. And then because you consider this operator AX, where X is just a real number, And you consider this essentially as a deformation of K by the identity. So if you insert X equals 0, then you get K back, and we know that the image of K was only a proper subspace, so that's a small subspace. But if you if you go to a point where X is bigger than 0, then you see that the image of this operator is actually the whole space. And the way you kind of like see this is by saying that the eigenvalues of AX, the eigenvalues of K, you look at the eigenvalues of K and see that -1 is not an eigenvalue, because you, by the assumption that K is a positive operator. And then use the Fredholm alternative to show that AX is injective, and then by Fredholm alternative, it's also surjective. So the point is here that you get this following picture. For X bigger than 0, you have a surjective operator, but at X equals 0, you get something that where the image immediately or appropriately jumps down to a proper subspace. And then you play around a bit and you find actually a symplectic form for which alpha, the omega flat actually is kind of like of this type for an operator AX. And then you see that the Taboo theorem can't hold, because the Taboo theorem would say that the rank or the image of this operator omega flat is constant, but these kind of counterexamples show that the image can jump or go down if you approach X equals to 0. So that's a counterexample for the Taboo theorem. And then you're a bit kind of like worried if you want to do a symplectic reduction, because the Taboo theorem is essentially one of the main steps that you have to do in the classical proof of, for example, the Malek-Guillemin-Sternberg normal form, which is then used for the singular symplectic reduction, where you can control the normal form theorem gives you then some normal form theorem for the modular space or for the symplectic reduction. So these two counterexamples that I showed have different flavor, or like the first one is more this analytic problems, where, for example, that you have to work around a bit with function analytic things. For example, this double orthogonals don't work anymore. And here, this example shows you that certain geometric constructions that you use from finite dimensions, something like the Taboo theorem, don't work anymore. So you have to find also really new proofs that are different, have different geometric input, and not just like sitting down and do a bit of functional analysis. And so that's essentially what I want to do now in the last remaining minutes, namely explain a bit which kind of new constructions we have to come up with, and which one can be kind of like what kind of problems can we solve via functional analytic methods, and where we really need to sit down and think about new geometric ideas to solve some of these problems. And the first one is what I like to call symplectic functional analysis, where we can apply some of the ideas that are well established from the theory of dual pairs to the symplectic world. And the idea is there that if you have a weakly symplectic form, that we change just the topology on our vector space that we started with to make omega strongly symplectic. And then we have to, or then kind of like we can translate this algebraic problems into a bit more topological problems. And then we can use some nice machinery to answer some of the problem questions that we might have. And for this purpose, we introduce the notion of symplectic topology. So we have a symplectic vector space V, and the topology on V is called symplectic if the image of this omega flat is given by all functionals that are continuous with respect to this new topology. So And the first observation that you have is that your original topology that you choose, for which omega was separately continuous, is symplectic in the sense if and only if your symplectic form is strongly symplectic, because then the omega flat is surjective, and then you get all of the continuous dual. So in this sense, symplectic topology measures how far you deviate from being strongly symplectic. And there are different types of symplectic topologies. And the easiest to describe is the so-called weak symplectic topology. And this is given by the semi-norms, where you essentially take the supremum over finite subsets of the symplectic form, paired with like elements of a finite subset. And this gives the weak form. And then there's some kind of maximum that is the so-called Mackey topology in the symplectic world. And the statement by Mackey and Arens is that every symplectic topology lies between these two topologies. So either it's stronger than the weak symplectic topology, but it's weaker than the symplectic Mackey topology. So you really understand relatively well which kind of topologies are symplectic and suitable or acceptable in this sense. And the so-called bipolar theorem tends to tell you then that a double symplectic orthogonal is given as the closure of the subspace that you took with respect to an arbitrary symplectic topology. So all of these symplectic topologies also have the same closure of linear spaces. So it doesn't matter which symplectic topology you choose there for the closure. So you see that that this viewpoint from by changing the topology is really helpful, because it allows you to translate these questions that are a bit more algebraic in nature, namely that you just take the double orthogonal, to something that you can answer with respect to with the help of topologies, by saying that something is a closure of a space. So that's usually really helpful. And one of the applications of this statement about bipolars or double symplectic orthogonals is the following: namely their bifurcation lemma, which is the infinitesimal version that you need to prove a symplectic reduction. So the setting there is that you have a symplectic G manifold and a momentum map. The momentum map is just as in finite dimension, is that you have the following equation that the momentum map has to satisfy. And then if you look long enough on this equation, then you see that there's the following relations, namely that the kernel of the momentum map is given by, and if you take the orthogonal of the kernel, then this one is given by the double orthogonal of the symplectic orbit of the Lie algebra. So that's here is the orbit acting on the chosen point, and then you take the double orthogonal. And similarly, you get an equation for the image of the momentum map, which is that you take the annihilator of the image, which is then a subspace of the Lie algebra, and you calculate that this one exactly the stabilizer of the point. So these two relations give you then are really helpful for the symplectic reduction. Namely, for example, the second equation tells you that if your action is free, then the momentum map is surjective, so that, for example, the level set is then submanifold, and then you can reduce by the free action, and then you get actually a symplectic manifold again. So that's the regular case. And the first statement is you need, in order to show that that the reduction of the symplectic form is actually a symplectic form again. And what you need if you kind of like follow in finite dimension is that this space here, that the kernel and the symplectic orthogonal, is exactly again the orbit again. So what you need here is that the orbit is symplectically closed. So in the sense that the orbit, and then you take double orthogonal of the orbit, that this one gives you the orbit again. And there are examples where this is actually the case. For example, if you look at this example of Atiyah-Bott, there are a group of gauge transformations that act on the space of connections, and then you can verify that the orbit is symplectically closed. So if you take twice the orthogonal, you end up with the same orbit again. But if you change like the setting slightly and consider all gauge transformations that vanish at a point, then these still act on the space of connections. But because you have this vanishing at one point, and you see that the closure of this orbit is the same as the orbit of the whole gauge transformations, actually. And you see also that kind of like would be one example where this requirement of the symplectic closed orbit is violated. And that's actually really important because you would like to quotient by this gauge transformation that vanish at a point, because they act freely. So that would be a candidate that you say, okay, we do symplectic reduction first by this group, and then we get some finite dimensional reminder that says, okay, what happens at this particular point? And that would be reduction by stages. So you would like to first quotient out by this pointed gauge transformations. And because that would be a free action, it turns out then this would be a symplectic space, and maybe even finite dimensional. And then you could reduce this study of this stratified space that you get of the moduli space of like connections by first reducing this pointed gauge transformations. But because the bifurcation lemma doesn't hold for this gauge algebra that are pointed, you can't actually use this nice strategy of passing to this reduction by stages. Okay, so after I told you all the stuff that doesn't work in infinite dimensions, and already hinted a bit on some particular ideas of what you can do to change your strategies, I want to come to the symplectic reduction in infinite dimensions. And the main ingredient in the symplectic reduction form is the Mallet-Gilman-Sternberg normal forms. So that's a normal form for the momentum map, and actually it doesn't really matter for the talk today how this normal form looks like in particular. So the idea is that you have an orbit of a chosen point, and you get a tubular neighborhood around this point, and you know exactly how the momentum map looks in this tubular neighborhood. But the particular form doesn't really matter. The point is that you know how this momentum map looks there, because then you can use this as a local chart of the symplectic quotient. So in this sense, it's really the fundamental ingredient essentially for the symplectic reduction procedure. And the proof of the Mallet-Gilman normal Sternberg normal form uses the equivalent Darboux theorem in finite dimensions. So, so what they do is you construct this normal form, and then you say, oh, the normal form coincides on the orbit, and then we use the Darboux theorem to say that it actually coincides in the whole tubular neighborhood and not just on the orbit. And so in this sense, the Darboux theorem, like the proof of this normal form, is actually symplectic first. So you first bring the symplectic form in a normal form, and then because you know that the action and the symplectic form are in a normal form, you calculate what is the momentum has to be in this normal form, because you know that it's essentially unique. And then you see that the momentum is carried along in a normal form. But as we saw before, in infinite dimensions, we can't use the strategy because we don't have any Darboux theorem. We don't know if the symplectic form can be brought in some kind of normal form. So the idea is a bit to look at what the people do in moduli space theories, and in particular the strategy of Kohanishii structures, and completely ignore the symplectic form. We don't know if it's in a normal form or not, but only concentrate on the momentum map, because that's what we're interested in the end. and want to construct a normal form for the momentum map. So the construction has 3 ingredients. The first one is that we prove some normal form theorem for arbitrary smooth maps, which is essentially similar to the theorem that if you have a surjective tension map, then you're locally a projection. So these kind of submersion theorems or immersion theorems is the first step, that you have kind of like something like this in infinite dimensions. And that you can do by using some form of inverse function theorem. And in my context, I used the Nash-Moser theorem, but they're also, like, depending on your functional analytic background or setting, you want to use a different one. So these ones can be established, and then you combine them with a normal form theorem for the action. And these ones are, for example, usually called slice theorems, which tell you that normal, like around one orbit, you find normal coordinates for the action. So, and if you combine these 2 things, the slice theorem and the normal form for the smooth maps, you get some kind of form, normal form for equivariant maps. And that if you then apply this with some symplectic geometry, and in particular only linear symplectic geometry, you can refine these ideas to get a normal form for the momentum map. So, so the proof then relies only on the inverse function theorem and then on the slice theorem, and doesn't use any Darboux theorem in its process. And the theorem that you end up with is something of the following form. So I'm not completely precise about all the assumptions in infinite dimensions, but the idea is the following, that we have symplectic manifold, and we have a momentum map, and we want to have a normal form around a given point, M, and we denote the value of the momentum map under M of this point M by mu. And we need certain, the first 2 assumptions about the actions. The first one is that this G and V action on the dual space can be linearized. And in finite dimensions, that's just like application of Bochner's theorem, because G and V acts has a G and V has a fixed point mu, and then Bochner's theorem tells you that it can be linearized in the neighborhood. So that's in finite dimension always satisfied, but in infinite dimensions we need to assume it. And then, as I said, the second assumption is that we need some form of slice theorem that holds for the action on M. And then the third assumption is that the orbit is symplectically closed, which was that the double symplectic orthogonal coincides with the orbit. And that's something that we need to control the symplectic, the momentum map in a linear way. And then the final assumption, which is kind of like the heart in some way, is similar to what Unit had yesterday, namely that we considered this deformation complex, where we have the first arrow is just the action, and then the second arrow is the momentum map. And because it's equivariant, it's kind of like a nonlinear complex. And what we assume is that if you go to the linearization, that you find some form of generalized inverse or parametrics or whatever you want to call it, in such a way that you can apply the inverse function theorem. So that's also similar to what Unit had yesterday for this rigidity, which is essentially assuming that this complex or that the symplectic reduction would be then just a bunch of points. So it would be 0-dimensional, because then everything that is in the kernel of the momentum map is in the image of the action. But in our case, it's actually not the case. So we really need to have like this term inverse or for this nonlinear complex in a whole neighborhood. So Unit was able to reduce this to a question on the Lie group, but that's no longer the case in our setting, because there's something that is happening transversal to the orbit. And in this, for this, we also need to have the inverses in the neighborhood of the points M. So that's really the point where the inverse function theorem comes in. And then under these assumptions, we have the statement that the momentum map can be brought into the molecular Sternberg normal form. So that's the infinite dimensional version of this normal form theorem. And then with the help of this, you can get also an infinite dimensional version of the singular symplectic reduction theorem. And you get all the nice statements about the stratification and that all strata are symplectic and so on. So these results also hold in infinite dimensions under exactly these kind of 4 assumptions that we have to impose there. And that's just like the end of the first journey. Namely, I think there's a lot of interesting open questions that are still in this area of symplectic geometry in infinite dimensions. And the first one is, for example, what I already mentioned. Can we do symplectic reduction also for this, where we drop this assumption that the orbit is symplectically closed? So, for example, I think that then we get something that is what is called quasi-Hamiltonian spaces or extended moduli spaces, which were introduced by Johannes Hübschmann in this context of reduction by pointed gauge transformations over a surface. And it would be really interesting to see how this can be generalized also to other contexts. Then I said that the Darboux theorem fails for weakly symplectic Banach or even Hilbert manifolds. So that means that contrastly to the finite dimension case, in infinite dimensions, we really have local invariance of our symplectic forms. But as far as I know, no one knows what kind of invariants these are. And I think like they could be related to these symplectic topologies that are introduced. So there's, as I said, these symplectic topologies in some way measure the abstraction from being strongly symplectic. So if there's a jump in the symplectic topologies, then this one could be the reason why the Darboux theorem doesn't hold. And then a bit more with direction to constructing quantum field theories. One way would be to first reduce to get a stratified symplectic space using these infinite dimensional versions of symplectic reduction. And then in the next step, construct the quantization by some form, for example, of geometric quantization or deformation quantization of stratified symplectic spaces. In a similar vein, it would be interesting to study this picture of geometric invariant theory, which is the algebraic dual point of symplectic reduction, also in infinite dimensions. And there's some nice applications in geometry, in particular to Kähler geometry, which is essentially in the work of Donaldson. And then one applications is also that an interesting particular case of symplectic reduction would be for cotangent bundles, which is usually what you encounter in applications, but which is also not even understood in finite dimensions to know completely how you can do symplectic reduction for cotangent bundles. And with this, I want to thank you for your attention.
Questions? So go ahead online.
Yeah, so my question would be this symplectic topology that you have. It is, you can just describe it as a pair in duality of vector spaces, because you just take you called it omega b of v, and this is a subspace of the dual. So you just look at this pair of dual spaces, and you could, I mean, what happens is, no, let me tell it a little different. For weak Riemannian metrics, with Mumford, we needed to introduce the notion of a robust weak Riemannian metric. And this just means that if you have the tangent bundle and you complete with respect to the Riemannian metric every tangent space, that you still get a smooth vector bundle. And here it looks somewhat similar, because if this dual, this symplectic dual, if it jumps, then you don't get a kind of bundle in here. So maybe this is a way to get your hand on this.
Yeah, I think that's a good idea. So there, yeah, I'm not sure if it's kind of like really if you should take the completion. You mean so you would take the completion with respect to the metric. So that means you take the, yes, that would probably be the Riemannian analog of the symplectic topology. If you take the, yeah, I mean, essentially everything that I said about symplectic forms, they also work for Riemannian metrics, because the schizometric part is not that important. Yeah, then it would be I think that would be then, for example, an obstruction, definitely, that if you take the completion with respect to the weak, say, weak symplectic topology, and this one is not a bundle, then you know that this one would be definitely an obstruction for the Darboux theorem. I'm not sure if it's kind of like already enough, that kind of like, yeah, if it's enough to assume that you get a bundle and then you know that it's the Darboux theorem holds. But it's definitely an interesting approach. Yes, and maybe I should also comment that I think, yeah, this Riemannian setting is also a bit similar. Where, for example, you could, for example, have similar approaches to, say, like the question of if you have a Levi-Civita connection or not, can be probably also answered in terms of these topologies. And if you say, kind of like know how these topologies jump to different points, then you know if, for example, Levi-Civita connections exist for a given weakly Riemannian metric and things like this. I think that's definitely an interesting approach to a few questions that are also in the Riemannian setting.
Yeah, this is also in this notion of robust Riemannian manifold, because there we also had to assume that the gradient of the Riemannian metric with respect to itself exists, and then the connection, the Levi-Civita connection exists.
Okay, yeah, thanks definitely for this pointer to the robust.
Yeah, I have a question. But before my question, the common feature between Riemannian and symplectic frameworks is that you have a duality pairing, right? And this is non-degenerate. So these two things will work basically the same. So in the Riemannian case, it's symmetric. In the symplectic case, it's antisymmetric. But the point is that you have a non-degenerate duality pairing. And that's what you have to deal with. I had a question about your terminology. Why is your bifurcation theorem called bifurcation theorem? Because for me, it refers to PDEs, and so I don't know where you take this term bifurcation.
I think the term bifurcation came originally from, okay. So the point is that you considered solutions of the Hamiltonian equations, and then you want to few, how was it? Yeah, so one way to view this, for example, is that the second equation is that if you have that the momentum map is the stabilizer is the abstraction for the surjectivity of the momentum map. So this means if you hit a point which has a stabilizer, then the level set of the momentum map changes, the topology changes, and it might get some kind of like cusp and stuff like this. And that's then kind of like a bifurcation phenomena for this for the topology of the momentum, the level set of the momentum map.
Thank you.
So,
are there any more questions? Okay, then let's stay to Diez then.